Hey, this is the video for the notes for Unit 5 in Algebra 3, Section 2.5, Transformations and Functions. This is the second video for this section. For the first video, we talked about translations. There are rigid transformations. You can move up, down, left, and right. Now we're going to work on reflections. Reflections are also a rigid transformation, meaning the function keeps the same shape. So if you have something f of negative x represents a y-axis reflection. I think of this a couple different ways. If I were to think of it graphically, and I were to plot the point 3, 1, so 3 is x and 1 is f of x. And I were to change the x to negative x, so instead of 3 it becomes a negative 3. This becomes the point negative 3, positive 1. So it's negative x, f of negative x. Graphically, we can look at the square root of x. So the square root of x plots a point at 0, 0, 1, 1, and 4, 2. Now if I wanted to look at y equals the square root of negative x, that means my x values become negative. So 0, 0 stays 0, 0. 1, 1 becomes negative 1, 1. 4, 2 becomes negative 4, positive 2. So that's what a y-axis reflection looks like. We can even look at this one more way, and I think I can explain why I like the square root of x better. If I look at the function y equals x squared, I'd plot the point 0, 0, 1, 1, negative 1, 1, 2, 4, negative 2, 4. If I did y equals negative x and I square it, well, 0 squared is 0. 1, negative 1 squared is a positive 1. Negative 2 squared is a positive 4. So you can see it comes out to be the exact same function. This function is symmetrical along the y-axis, so it's boring to show you something like this with a y-axis reflection because you can't tell the original from the function itself. When you have a y-axis reflection like this, when the function is symmetrical, this is an even function. And it's something we'll study in other classes. It's in this book, but I don't usually cover it in Algebra 3. This negative f of x is going to be an x-axis reflection. So if I look at it this way, start with the point 3, 1 again. This is x, f of x. This is saying that I want to change the y value. Negative f of x means I want to change the y value. So I want x negative f of x. So I'm going to plot the point 3, negative 1. Becomes f negative f of x. And you can see it reflects over the x-axis. If I do this with the square root of x, 0, 0, 1, 1, 4, 2. Here's y equals the square root of x. If I want to graph y equals negative square root of x, I'm going to change all the y values. So 0, 0, and then 1, negative 1, 4, negative 2. That's what it looks like. And then one more. So if I start with y equals x squared, I did that function a second ago, 0, 0, 1, 1, negative 1, 1, 2, 4, negative 2, 4. If I kept going, it'd be 3, 9, negative 3, 9, 4, 16, negative 4, 16. Now what I want to do is I want y equals negative x squared. The difference, the negative was inside with the x and then squared. This one, the x is squared and then the negative on the outside. So it means I'm going to change all the y values. So 0, 0 stays 0, 0. 1, 1 becomes 1, negative 1. Negative 1, 4, negative 2, 4 becomes negative 2, negative 4. And this reflects down this way. Most students are comfortable with this x-axis reflection because they've seen it before. The y-axis reflection is a little bit different to look at. Okay, the next one we're going to do is now going to be a non-rigid transformation. These are the ones that students find a little bit more difficult to handle. So just take your time, ask questions when you have questions. So what we're doing is we're looking at the CF of x. CF of x means the C in front of the value is going to be a constant. It's going to be some kind of a number. If that number is greater than 1, it is going to be a vertical stretch. So for example, start out again with my y equals the square root of x. 0, 0, 1, 1, 4, 2. If I put a number in front of this function, so y equals 2 square root of x. Let's do it in red. That means I'm going to take all the y values and multiply them by 2. So 0, 0 becomes 0, 0. 1, 1, I'm going to multiply the y value by 2. So it becomes 1, 2. 4, 2, multiply the y value by 2, I get 4, 4. There's your vertical stretch. I'll do another type of function. Okay, the function I'm going to use is y equals x cubed. So if I put a 0 in, I get a 0 out. 1 cubed is positive 1. Negative 1 cubed is negative 1. 2 cubed is 8. Negative 2 cubed is negative 8. So this is what an x cubed function looks like. If I want to stretch that function, say y equals 3x cubed, as long as its number in front of the x cubed is greater than 1, it's going to be a vertical stretch. So 0, 0 stays 0, 0. Instead of 1, 1, I'm going to multiply the 1 by 3 and I get 1, 3. Negative 1, negative 3. Now is when it gets really hard. The next point would be 2, and then 2 cubed is 8. 8 times 3 is 24. It's going to be way up here. I'm not going to be able to get to it. So I'm just going to do this. So you can see it's being pulled. Imagine you're taking 2 strings and you're pulling it in this direction. Just like this. Pull it, pull it, pull it, pull it. It's stretching it. Well, anytime you stretch something vertically, it appears to also shrink this way. So from the equation, I can tell that this is a vertical stretch. If I were just given the graph, I wouldn't know. Now for a vertical shrink. It's still, you're multiplying the y value, but now the value that you're multiplying the function by has got to be a number between 0 and 1. I don't use numbers less than 0 because then we start looking at reflections. So as long as it's between 0 and 1, like 1/2, 0.3, 7/8, any of those are going to be a vertical shrink. I'll give you a couple examples. Back to my square root function. So this is y equals the square root of x. And let's pick y equals 1/2 square root of x. So I'm still going to have 0, 0. And then instead of going to 1, 1, I'm going to have 1, 1/2. Instead of going to 4, 2, I'm going to have 4, 1. I'm cutting the y values in half. So you can see it has pushed it down. And instead of using a cubic function, let's use an absolute value function. So if I had y equals absolute value of x, and I plot the point 1, 1, 1, 2, 2, 3, 3, negative 1, 1, negative 2, 2, negative 3, 3. So all these functions you studied in Algebra 2. Let's make this y equals 3/4 absolute value of x. That just means I'm going to start at 0, 0 again, but when I put a 1 in, I'm going to get a 3/4. When I put a 2 in, 2 times 3/4 is 6/4, which is 3/2. When I put a 3 in, I get 9/4. 9/4 is 2 1/4. And the same thing on this side. So it's a vertical shrink. It's pushing it down. Same time, it looks like it's pulling this direction, but this one tells me that it's shrinking it down. The vertical stretches and shrinks are more common. They're easier to work with. If you're looking for values, it's a lot easier to work with vertical stretches and shrinks. But we also have horizontal. Horizontal stretches and shrinks are something that students tend to struggle a little bit with. If I have a constant now inside with the x, anytime you have a number inside with the x, you're changing something along the x-axis. So that's how I know it's going to be a horizontal stretch and shrink. It's opposite of what you would think. If the number being multiplied by the x is between 0 and 1, so like 1/2, 3/4, 0.7, it's going to be a horizontal stretch. Give you one example instead of giving you many. So I would start with my y equals the square root of x. So if I do this and then square root of x, 0, 0, 1, the square root of 1 is 1. And then the square root of 2 is a decimal, square root of 3 is a decimal, square root of 4 is 2. That's why I've been choosing that point. And then you keep going, but the next one I would pick would be 9. The square root of 9 is 3. So I'd pick the point 9, 3. Not a very good picture, but you get the idea. Now if I take these and change this, x square root of 1/2 x. So I'm still going to have 0, 0. But when I put a 1 in, I'm going to get the square root of 1/2. Not a very good point to plot. So if I put a 2 in, 1/2 times 2 is 1. I'm going to get the square root of 1, which is equal to 1. So I'm going to have the point 2, 1. If I put a 4 in, I get the square root of, 4 times, 1/2 times 4 is 2, the square root of 2. That's about 1.4, I'm not going to worry about that. Next good number I put in is if I put an 8 in. 1/2 times 8 is 4, so I'm going to get the square root of 4, which is 2. So all the way out here at 8, 1, 2, 3, 4, 5, 6, 7, 8, I'm going to plot a 2. So this one looks like it's getting pushed down, but it's really getting pulled, taking this and pulling it, and it's stretched it horizontally. The next one that's horizontal is going to be a shrink or a compression. So if I go back to my function, 0, 0, 1, 1, 4, 2, 9, 3. Looks like that. Go back to my table. 0, 1. I'm only going to plot 4 and 9. I'm not going to worry about all the other numbers. I could go on. I could plot 16. So the square root of 0 is 0. The square root of 1 is 1. Square root of 4 is 2. Square root of 9 is 3. Square root of 16 is 4. And that's where I get all these points. Now let's look at this as x square root of 2x. So 0, 0 is still the same point. 1, I have the square root of 2. Not a very good point to plot. If I put a 2 in for x, 2 times 2 is 4, the square root of 4 is 2. So I would plot the point 2, 2. If I did a 3, I'd get 6. If I did a 4, I'd get 8. 5, I'd get 10. 5, I'd get the square root of 10. Not very good numbers to plot. 6, 7, 8. Well, 8 would be the next good one. If I put an 8 in, I get the square root of 16, which is equal to 4. So it would be about up here. So that's what it looks like. It is actually shrinking it. It's pushing it together. And as it's pushing it together, it appears as if it's stretching up. We'll focus mostly on the vertical. If you go on to another math class, we talk more about this horizontal. Now, as I've been doing these, I've been introducing different, well, not introducing functions, I've been talking about different functions. These are all called parent functions. The identity function is what you recognize as a line. It's a specific, goes through 0, 0, and has a slope of 1. The equation would be y equals x. My domain is all real numbers, and my range is all real numbers. If I were to do transformations with this, this is why I feel point slope form is a lot more useful. If I look at it this way, so I had y minus 2 equals 4x minus 1. I know that this function is being vertically stretched by 4. It is moved right 1. And if I move this 2 over, this is saying it's gone up 2. Absolute value function. It's like taking two lines and putting them together. 0, 0, 1, 1, 2, 2. So this is y equals absolute value of x. My domain is going to be all real numbers. And my range is going to start at 0 and go up. 0 to infinity. Quadratic function. So y equals x squared. 0, 0, 1, 1, 2, 4. It's symmetric along the y-axis. So it looks like that. So just like the absolute value, my domain is all real numbers, and my range includes 0 and goes towards infinity. My favorite, the square root function. So y equals the square root of x. My domain starts at 0, including 0, and keeps going towards infinity. And my range is the same thing as my domain. And then the cubic function, which I also did previously. 0, 0, 1, 1, negative 1, negative 1. And then it's all the way up here at 2, 8, and 2, negative 8. So it looks like that. So y equals x cubed. My domain is going to be all real numbers. And my range is all real numbers. And the last one, and all these are also in your textbook, is a cube root function. The cube root function is the inverse of the cubic. So 0, 0, 1, 1, negative 1, negative 1. But instead of going to 2, 8, it's going to go to 8, 2. 1, 2, 3, 4, 5, 6, 7, 8. Squeezing it in there. They look very similar, and we're going to actually study inverse functions in the next unit. So it would be y equals a cube root of x. My domain is all real numbers, and my range is all real numbers. And that's everything for this unit. We'll spend a couple days on this unit, not because it's difficult, because I don't feel that it is difficult for most students, but it's just, there's a lot going on with this, and the more practice you get, the better you will be.